Well, Matrix, welcome back to Matrix Uploaded. Welcome grade 10s and 11s. Don't panic. This is really focusing on matric work, but grade 10s, you can learn something, especially about x-intercepts, about graphs, and you can see what's coming. You're going to be doing, you've probably done this already. You've looked at hyperbolas, parabolas, all those graphs. If not, it's coming. Of course, grade 11s, you know this, but now there's other curves, the cubic things, and of course, this is really matric focused now. We're focusing on the matrix here. Okay, now have a look at the cubic function matrix. Instead of a parabola, now we get an x cubed. Now, just to revise quickly, you've probably done this already, but some important principles, and then we're going to actually do two examples in this lesson. Intercepts with the axes, the y-intercept, we let x be equal to naught. Okay. And, sorry, the y-intercept, we let x be naught, and the x-intercept or intercepts, we let y be naught. Now, that is a fundamental principle all the way from grade 9 even, and grade 10s, whenever you want to get, for your graphs, a straight line or whatever, the x-intercept, you let y be naught, y-intercept, you let x be naught. Now, of course, also the matrix, if you remember, with stationary points, what is a stationary point? Well, it's really turning points, if you think about it. If we get some ink color here. Remember, if you've got turning points, what happens at a turning point is the gradient of the tangent is naught. And remember, gradient, a stationary point is where the gradient of the graph or the gradient of the tangent is naught. So at that point where the graph turns, that's a maximum. You can have a minimum there. Again, the tangent is going to be, you know, restricted there to that place, and the gradient is naught. So the important thing is, what do we know about gradients? At a stationary point, the gradient is naught. That's a very powerful tool in calculus. Okay, and a point of inflection, it's really where the graph changes from happy to sad or sad to happy. They call it concavity, but it's actually easy. You'll probably see with a cubic graph, it kind of does this. It goes up, it comes down, that's sad. Now look at that point there. Then it suddenly changes to be happy. That point there is what we call a point of inflection, from sad to happy. And some very important principles emerge with that. At a point of inflection, the second derivative is naught. Now, the second derivative, it's quite a complicated story. There is an easier way of actually doing it, which is more sensible. And we'll pursue this as we go along. In fact, it's about the x coordinates of the turning points, what you do with them. But remember the principle the f doubled, the second derivative is equal to naught. Okay, now what else do we need? That's what it's saying. It says the sum of the x coordinates, if you add them up, divide by 2, will give you then the x of the point of inflection. But don't panic with that. We're going to get into that. Let's start looking at an example now. Okay. Now remember, back in Matrix Uploaded, we did the factor theorem. I called it the smiley face. Your schools would have solved cubics by now as well. If you've done calculus, you would have definitely come up. I'm going to use a specific method that we use. There are many other ways: long division, synthetic division. We're going to use inspection. Okay, it's one method, but if you know it, that's great. If you go back in time to the other Matrix Uploadeds, you can actually see what we did. But let's just have a look at this. The first thing with this one is, by the way, its shape. By the way, if that's 2, something very important about its shape is if that coefficient, if this number here is positive, the cubic graph looks something like this. Okay, it looks something like that. If that was negative, so if you had, say, negative 2x cubed, whatever, it goes like this. Okay, so just be careful. So this tells us something about the shape of the cubic. It's always good to know what it looks like. The y-intercept is if you let the x's be naught. Remember, with y-intercept, you let x be equal to naught. Then, of course, all of those go to naught, and you're left with -4. So that's the y-intercept. Hold on to that. Okay. Now, let's have a look. What do we get as we get the x-intercepts? We're going to let the y be naught, and of course there's a common factor of 2, so let's divide. Now this unfortunately is not an x squared, so it's not a parabola. So what do? Is we're going to use the factor theorem, or the method of solving cubic equations. I'm just going to briefly revise how I approach this. Okay, you might do it differently, but let's see different methods. Let's pursue this a bit. The one way is to say, okay, what we do, and I think in all methods, what you would need to do is get the possible answers. And if you take plus minus 1, plus minus 2, these guys here are what they are. They're solutions to the factors of that n number will be a possible solution. Now check the slide out. If you've got plus minus 1, plus minus 2, the factors of that, we've got to test some of those. Now if I try x equals 1, I don't think that's going to be of any help, because look at this, 1 cubed minus 3 times 1 minus 2 is not equal to 0. That's 1 minus 3 is negative 2 minus 2. If you try x equals minus 1, let's see what happens. Minus 1 cubed minus 3 times minus 1 minus 2 is, guess what, is 0. 3 minus 1 is 2. And that's brilliant. And you probably remember now, once we've got that, is that that's a potential answer. So we've got x equals minus 1. Remember, we get a factor there. And now, I want you in the break to pursue your method of now factorizing this. Okay, we've done the standard one. You've got long division, synthetic, or the smiley face. Give it a shot, and after the break, we'll continue with this cubic graph. Okay, stay with us on the Tricks Uploaded.